Good. Class, today we're going to go through, there'll be two halves to this lesson. It's 1 hour 40 minutes, it's going to be long, and we're going to split it up into about 1/3, 2/3 kind of section. So the first 1/3 we're going to go through this thing called standing wave. And before I show you what a standing wave is, which I'm going to show you over here, this is like one of the first time I'm bringing a computer here. So sever the moment. It may be the last time for this year. So the reason why I bring this is because I feel that it's useful. I use PPT because I feel that it's useful, not because I have to use it. So later on you'll see why. Because you need to visualize how a standing wave looks like. Now, but I'm going to go back to the principles that we've learned beforehand, and then we're going to build from those principles. Now let's see how much you remember. No worries, no complex numbers, no weird stuff, yeah? No phasor diagram today. So let's take a look. For constructive interference, what do you say is the path difference? N lambda, exactly. And n is a whole number, yes, correct. And for destructive interference, path difference must be equals to n plus half, not half, yeah? And I've said this thousands of times already. What is the assumption for these conditions to be true? Sources in phase. You must verbalize it clearly. Yeah, it's not wrong. Just sources are in phase. I've said this beforehand as well. So what happens if the sources are out of phase? The conditions get swap around. Yes, correct. So make sure that you check whether the sources are in phase or not. If it is not mentioned, standard approach is always to assume that the sources are in phase. Okay. Now let's develop from here. Consider two sources S2 and S1. We have always talked about the pattern over here. Now we're going to focus on the pattern that is in between these two. Now let's consider a point right in the middle where it is right in the middle of those two sources. Now what's the path difference at this point? Path difference equals to 0, which actually tallies with this condition where n is equals to 0. So what do you expect over there? Constructive, yes, correct. So this implied as constructive. Now let's consider a point which is lambda upon 4, which is called point x over here. Now can you see that the distance, if I call this L, then the path difference over here is equals to L plus a quarter minus L minus a quarter. So the source on the right will have to travel a quarter wavelength more, the source on the left will travel a quarter wavelength less. So therefore, the path difference is equals to half a wavelength, which means that it is exactly. Now, can you see the sequence or not? Whenever I travel a quarter of a wavelength towards the left or towards the right, I'll go through a series of loud, soft, loud, soft, loud, soft. Now, essentially over here is what we have. What we have over here is essentially a standing wave. Now at this point of time, I'm going to show you what exactly is a standing wave so that you can see it for yourself, so that it becomes more three-dimensional. So let's take a look at these slides. The applet, not even the slides. Let's take a look at the applet. Let's see whether it comes up nicely. Am I supposed to press the on button or something like that? So is the projector on? It's supposed to be on. I press on and it says Sing Select PC. Is it on? Can you just press the on button? Okay, let's take a look. This is really important. You need to... It's kind of weird when the battery is actually 100%, it says battery is low. I don't know which battery is low. As we're waiting for this to come up, anyone has any questions to ask regarding the phasor diagram or the complex numbers thing? Still indigestion? Still conceptual indigestion, constipation? Any questions from that lesson yesterday? The amazing lesson yesterday. Okay, ready? Now let's take a look. The wave that you see over here, it appears red over here, but it doesn't appear red over here, so just try to imagine that it's red. Can you see that the wave is moving towards the right? It's all okay. I hope you can see that the wave is moving towards the right. If you can't see that the wave is moving towards the right, there's something seriously wrong. So what happens when the wave hits the end? It gets when the sound wave hits the wall, it gets exactly reflected back. So this is the wave that gets reflected back. So still okay? So if I send a sound wave towards the wall, there are two waves that are coming together meeting each other, which is exactly the same as what I did just now where there are two sources sending waves this way. Okay, the context? Okay, good. Now let's take a look at what happens the resultant wave. Now, I just want you to spend 10 seconds. Try to imagine what is the resultant wave going to look like. Just 10 seconds. Try to imagine when this adds with this. Just 10 seconds.
Amplitude double.
6, 5, 4, 3, 2, 1. Okay, this is what happens. There is a mathematical explanation, but I shall spare you from it. This is what you see, which makes sense if you take a careful look. If you take a careful look at this and this, I'm going to mix up this tree and pause. Now, can you see that at this moment the two waves add up?
Yeah.
Right? And then at this moment, if you were to go through, wham! This is the moment where it cancels out totally. But even though as it cancels out totally and adds up maximally, can you see that there are points where the wave amplitude is always 0? The points where they are marked?
Destructive.
A or N? N, exactly. So these points over here are what we call nodes. Obvious reasons why they are labeled N. And those points where the amplitude is the maximum is what we call antinodes. So these are the two things. If you go back to the thing that we've been talking about just now, now these positions where there's maximum amplitude is what we call the constructive interference, which is where we have the path difference equals to 0 or 1 lambda or 2 lambda where your constructive interference happens. And these positions where you have your N are the positions where the wave meets destructively, where the amplitude is always 0. So can see that we are applying interference technique into this thing called interference. There is a full mathematical derivation, but I think you'll be equal. Let's spare you from that. Okay? When the time is opportune, when I think that your mathematical abilities is mature enough, I'll show you. It can be done. The problem with this is that because the amplitude actually varies with x and it varies with time. So it gets a little bit difficult when you actually have two axes to handle. Yeah? So just imagine, just remember this thing. It's a little bit hypnotic. If you look at it for 1 more minute, you're going to fall asleep. So let's not look at it too long. Can? So have that picture in mind. When I say standing wave, come to your mind, this one. Look for another 10 seconds. You're going to get hypnotized if you look at it too long. Something good for you to look at if you can't sleep at night, though, right? Let's look at it. And then after 10 seconds, you Okay. Right. Now, the next thing I'm going to go to is this. Can you take out your notes on the standing wave 4.5? It's under 4.5. Can you bring out your notes? You don't have it, or it's like gone for good? It's like, where is it? It went into the black hole and disappeared. 4.5. I'm going to make strong references to the notes, so you must have your 4.5. Yep, there's 4.5, which is called standing wave. Tian, if you don't mind, can you switch off the thing? Thanks. I don't want to be in the spotlight. I think you're the only one who is tall enough to, yep.
Need a when? Wait, hold on.
Okay, thank you. Excellent. So, point number 1 that you need to know, exam things that you need to really know because it can come out as an exam question, is how is a standing wave formed? Now, in your notes, do you see this whole chunk of words that says standing wave is formed when two waves of the same kind traveling in opposite direction with the same speed, same amplitude, same frequency meet and superpose? Do you see something like this? Yep. Can you put a lot of stars around it so that it's clear to you that you need to know this? Okay, the few things I'll look out for, basically waves of the same kind, speed, amplitude, frequency, travel in opposite direction, meet and superposed. Almost same everything, just don't say same velocity, because same velocity and traveling in opposite direction doesn't come together. Yeah? It's oxymoronic if you say the same velocity and traveling in opposite direction. So like what you saw just now, same wave, opposite direction, meet and superpose. That's when you form the standing wave. I'm going to explain to you the difference between standing wave and progressive wave. Then we are more or less done, actually, for the day. Okay, relax. All is well. My goodness. And to make things worse, I got a feeling that it's because the film hasn't been torn out. Ha! I'm right. It's actually a protective film. My guess is right. After teaching for 12 years, it's spanking new. It's spanking new. No. Hang on. It has been changed recently. So, oh, it feels so satisfying. It's like, actually, we should have a room like this for people to just a small little room beside the counseling room kind. Yeah. It's actually very satisfying. Or probably a room full of those kind of bubble wraps. For people to de-stress. Right. This is electrostatics, right? This is Oi. Oh. No, this is the remaining. Hey, this is interesting. Let's see how long it's going to get. Let's see how long it's going to get. This is the irritating part. It tends to get stuck to your hands. Okay, good. All right. Okay, let's come back to this. Yeah, it's fine. I didn't say anything weird, right? Other than making the suggestion of having this in a bubble wrap room. Okay, so standing wave and progressive wave. So you need to know that there are a few major differences. Okay, probably I should add one more column. And there are many other differences. I think there are 5 in your table, if I'm not wrong, if you refer to your notes, 5 or 4. I'll just surface a few key ones. Because usually you're asked to state 2 or 3 differences. Now, energy, you need to know that there is no net energy transfer. Please be very careful that it is no net energy, not no energy. You'll be marked wrong if you say no energy. Net energy transferred. Amplitude-wise, varies from max at antinodes to min at the nodes. Yes, Balaji and Aditya, any problem? Any issues? Okay. Same for all points. Now, as you saw just now from the applet, the amplitude varies for a standing wave from the minimum at the nodes to the maximum at the antinodes. Any issues? Again, sorry? Hang on. Yeah, normal wave, exactly. The wave that you saw, the blue and the red just now. Nodes, I assume nodes, antinodes. Yeah? But for progressive wave, as the wave moves past, all points will hit the same amplitude. This is very different for standing wave, where if you were to be at a certain point, you have maximum amplitude, you move to the left or the right, you get minimum amplitude, as you saw in the animation just now. Yeah? The next thing is a little bit more tricky, but I have to go through this because it is a very popular question at MCQ for IB. Now, remember just now when you look at the standing wave, when one particle goes down to the minimum, this one goes down to the minimum. So the particles within, let's say, A, B, C, the particles between A and B, they are all in sync. They have different amplitudes, but when one point reaches the equilibrium position, all points reaches equilibrium. And when one point reaches the negative maximum, all points reaches the negative maximum. So they are in sync in terms of their movement. So that's what we meant when we say that all points, for standing wave, all points between 2 adjacent nodes are in phase. So that's what we meant. Any points between 2 adjacent nodes, they are in phase. That means they move up and down together in layman terms. Yeah? When one reaches the amplitude, all reaches amplitude. But for progressive wave, it's different. For progressive wave, all particles within one wavelength, they are not in phase. Now what do I mean by this? It means that you will not be able to find 2 points within one wavelength that have the same displacement, same direction of velocity between one wavelength. You can't do that. You won't be able to find. So that's the difference between progressive wave and standing wave in terms of phase. One last point is that any points over here and any points over here, they are out of phase. What do I mean? Let's say point 1, point 2, point 3, point 4. Point 1 and 2 in phase. 1 and 4 out of phase. 2 and 3 out of phase. But 3 and 4, they are in phase. So any 2 points within the same half will be in phase. Any 2 points that are in different halves, they'll be always out of phase. That means they'll always be traveling opposite direction. Yes, please go ahead. You mean this one? Yeah, then this one and this will be in phase. Yeah, this and this will be out of phase too. Can? Oh, 2 adjacent nodes means this one and this one. Which one and which one? Let's say this is A, B, C, and D. Which one name? Mm-hmm. Oh, okay. Beyond that, then this, okay. 2 adjacent nodes means, say, for example, these two. So all points between these two will be in phase. But these 2 points, they are no longer, okay, between these 2 points, these points are in phase. But these points, they are out of phase with this one. Yeah, if you go even further, then these 2 points over here, all points over here, they're in phase. But this one is out of phase with this one, and this one is out of phase again. That's why it is in phase. It's out of phase twice, so it goes back to in phase. Can? Cool. Right. I will stop here today because the next half I'll show you the 3 different ways that you can produce standing waves. And you may want to read forward the 3 different situations I'll go through with you. So I'll stop here today for the lesson wise. I will move on to practical. Okay.